If the ft is a function of time, so the x-axis is what? T, and y is what? Ft. And from 0 to infinity, t's value is what? 1. Call 1 a unit number. And what about the situation when t is smaller than 0? Think about time starts from maybe negative. We define when t is smaller than 0, the ut or the ft is what? 0. So the whole figure, the curve becomes like a step, like that. Take a step, right? Step up. And here, think the final value is 1. It's a unit number, unit value. So we call this a unit step function. This is what is a step function. So the mathematic dispersion is here. When t is smaller than 0, ut, or we say ft, is 1, 0. But when t from 0 to infinity, ut equals what? 1. Then, how to get the Laplace transform for the unit step function? How to get the Laplace transform for this one? Refer to the what? Definition. So how can we use definition to solve the Laplace transform for this function? It's easy. This is definitely do the integration from time domain, time from 0 to infinity. And here ft should times what? E to the negative power ft infinity, right? So once we write down this definition, then we can write the definition of a step function. Here, Laplace transform of a step function. Here, so how about ft here? We place the step function here, and instead of ft, it's 1. It's just 1. Why? Why? Because we have two values, 0 and 1. But the y here it's 1, but not 0. Yeah, it's the limitation. It's from 0 to infinity. Then we no longer think about the 0 thing. We just take 1 as a value in t. So we write 1 here. Then how to solve the integration of this? Good at math? See, we have x here, it's what? X, right? So we want the d is what? D minus ft. So this are the same. So how to get d minus t? We should first take a 1 divided by x times minus 1. Take it out of the yeah. Then things become like that. We just do minus 1 divided by x times e to the negative power ft from what? 0 to infinity. And we can rewrite this as this one. Then have e to the negative x times infinity. What is the value of this? 0. 0 minus this is what? 1. So we get a minus 1 here. Minus 1 times minus this, then we get 1. 1 divided by x. So this is what? The Laplace transform of a unit step function. Maybe I don't think it's that complicated. So if you cannot write the whole solution process yourself, then try to memorize the results. So because it will be required you to use the result to solve some problems. So you don't, every time you use the result, you don't need to rewrite the whole solution process. As long as you remember, it's okay to just use the results. Let's think about another situation. How about the step value? It's not a unit value. Maybe the output value, the final value is not 1. Probably it's 2, 3, 10. So then what is the Laplace transform of that kind of different value? Step. If the amplitude of ut is not unit, that is to say, you have a value maybe 1, 2, 3, or 1. The Laplace transform of the unit, not of the step function, if the amplitude is not 1, then r should be 1. Instead of 1, we should write r. Because here you have r here, right? Then you can take r out of the integration part. Then you can still get r. So if the amplitude of t is not unit, then write the amplitude. Okay. Ramp function. Easy. See, this is the description, mathematical description of a ramp function. When t is smaller than 0, then what? Get 0. When t is equal or greater than 0, ft equals t, then you can write, you can get the figure of the ramp function. It's a slope rate. And how about the degree of the slope? So we get t when x equals t, then y equals t, right? This is, and this, when the degree here is 45, then we call this situation the unit ramp function. As long as the degree changes, then we can no longer call it the unit, because time tends to t, final value of the t, not t. So how about to get the Laplace transform of this function? Which one would you see? First, we should write down the definition. Okay? Definition. This is the definition of what? Laplace transform. Then how about t? What's the value of t? Since we just consider 0 to infinity, so t we should write t. Then how to solve the integration of this? First, we should change t to fft, right? Then we have same as the previous situation. We should write -1 divided by s here, then we can get a d minus ft here. So minus ft minus ft. Then this whole integration will be changed to this. We can take the whole coefficient, right? This coefficient can be taken out of the whole integration part. Then the integration becomes from time domain 0 infinity t d e to the next power n. Then how to use solve this? To learn the rules integration by part. So we can use the rule integration by parts here. Yes. This is the definition of how to use integration by parts. So let u equals t. dv means de to the next power of t. And then du is what? Just dt. And v is what? E minus ft. And the whole thing is what? It's integration into dv, right? So we should write uv here. This is uv. Minus And here we get a minus and a minus here, so we get what? A plus here. Plus and integration of v du. This. And count it out, we can get this is 0, of course, right? This is 0 plus 1 divided by x times minus 1 divided by x and e to the next power ft from 0 to infinity. Then we can get 1 divided by x squared. So this is the result of the Laplace transform of a unit graph. How about it is not a unit? How about the magnitude of ft is not? So we may get a coefficient of maybe a times t, a is a coefficient. A is a constant. Then fs will change into what? A is still a coefficient. You can write a here, right? Then you can take a totally out of the integration. So after we do the integration, just times a. Then fs equal to a divided by x squared. Still, at least try to memorize the results. Okay, let's come to the third function, pulse function. What is a pulse function? So see the figure here. When t is not 0, the value of the pulse function is 0. Otherwise, value is what? Infinity. That is to say, from this domain or this domain, pulse function equals 0. But with the domain only very close to t equals 0. Very, very small domain here. And then we have a very large value. So we call it pulse. That's the value at the t equals 0. The value here is very large, 10 to infinity. So this is the unit pulse function. So the figure here is showing this should be very big. And from this and from here as well, it's 0. And the characteristic of the unit pulse function derivatives are as follows. First one is you do the integration from time domain from negative infinity to infinity. Consider the whole time domain. Integration of derivative times derivative in time domain as well. It's 1. And a definition here. If we think about a function gt here, we let derivative times gt and do the integration in time domain from negative infinity to infinity. Then we get g0 equals to this definition. G0 means when t equals 0, we get gt here. It's a function which is trying to solve the problem to name a gt. And g0 represents the initial value of the function gt at the time t equals 0. And how to get a Laplace transform for this one? Okay, good. We can have a rest and you can think it over. And we'll talk about this later.
We have how many students here on campus? Like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. But now we just have 1, 2, 3, 4, 5. How about others? How about others? Still sleeping? Oh, yeah. Maybe next time you should ask them to come together. So is that hard to ask them to come to the class? Oh.
Any more? Start. Just take that. So what's the question? No. No, this person is not using that. We use this as two. Yeah, and it will be summarized in the table. In the textbook, maybe we can refer to the table. Oh, the bookshop. Here's the table. Laplace Transform. And this one don't have to do by the whole people. That's how problem is. And that uploaded the version of the scan version of the book and reach out group. If download, 黄老师 uploaded last week.
You buy this?
Yeah, the whole scan version. You can download it and
Oh, it's hard. Like so close. You didn't see. Wait.
then what you thinking of something?
Okay, let's continue. How to get the Laplace Transform from problem.
Well, the math thing makes it difficult, but try to wake yourself up. Because the pulse function occurs a jump, right? She is the special situation we considered before. So we should separate the domain from minus 0 plus t. We just consider the definition domain from 0 to infinity. That is to say, to 0 plus to infinity. Cannot reflect all characteristics and interval of 0 minus to 0 plus. So consider the formula. Can you get the book, the scanned version of the book? Last week, Kalash uploaded in the WeChat group. You can download and refer to these two formulas. And then, so by the definition here, we will write from 0 to infinity, right? Let's see, since we should consider the small domain from 0 minus to 0 plus, then right here, and then add another domain from 0 plus 2. Because we have definition of the pulse or infinite pulse function here, so when t equals 0, the value is infinity. But otherwise, the value equals 0. Then we can write it. Okay? And how about the cursor jump? Think about this definition. We name a function gt. And when t equals 0, we get g0 subdivision. So we can rewrite this part into this. And when t equals 0, actually this one equals what? G0. G0 equals e to the next power e to the next power st, and at what special point t equals 0. Then to let t equal 0 here, then how about this whole thing? This one. So you see the Laplace transform where the unit's pulse function is just okay. The results with the red line, you should memorize.
How is your equal?
This one should refer to the definition of the these three right here, right? And if you compare these two, you can find what? Yeah. These two definitions. The same. So GT just what? To the next element. Okay. Exponential function. But we have index of it's what? 8. T called exponential function. How to get a Laplace transform for this? Really good. Yeah. Okay. It's the easiest one as well. You just write what? E AT here, then we get index AT minus 19. Then one over A minus A. Yeah. We can write this together. Then the index change into what? We take minus out of the then we get minus x minus A times t, right? Then you should rewrite t like this. How to change t like this? First, you should what? 1 divided by this one. Then you can write this one instead of t. Then the whole thing becomes this, right? And from what? 0 to infinity. So this one, calculate this one. 1 minus 1. Minus 1 times the minus, then you get 1. 1 divided by x minus a. So this is the Laplace transform for the exponential function. Maybe it's this one.
Then we come to a complex one. Trigonometric function. Sine, cosine.
Find the Laplace transform for sine function. Sine omega t. Omega is what? Frequency, right? Then how to work out this? This is a lot more complicated than the previous one. First, of course, you can write this down because according to the limit, right? Sine omega t. Then for the next step. Have you ever wondered? No? Not the exact pronunciation of this name. Eula. Some direction tells me it's Morla or something. I don't know what's the exact. Eula. Euler formula. According to the Euler formula in the complex, then sine omega t will equal to this one. J is what? The domain is what? Complex domain, right? So sine omega t can be written as this. And you replace sine omega t by this. So we get Laplace transform for sine omega t like this. And to make it easy, because it's just a function of what? E index with index. So the whole process, you can, if you want to know, you can go through the whole process after class. But then after the solution process, we will get the results. This one. Try to remember this one, this result. Sine omega t, Laplace transform of sine omega t is what? Omega divided by s squared plus omega squared. This is what we reference. And you can go through this process after class. Just by Euler. It's not that complicated as shown once you do yourself. Then how about cosine? Cosine. Is that right? Still use what? Euler formula. Then you replace cosine omega t what this, right? And it's all about the E and its index. And if you do the integration, you will find out the Laplace transform of cosine omega t. So what's the difference of sine and cosine? Sine omega and cosine y.
Yes.
Right? So these two, memorize these two, and say to tell. Then, how about power function? Follow Laplace transform for power function. X equals t squared divided by 2. At least, according to the definition, you can at least write down one equation that you right? Yeah. Oh, you're really good at math. Yes. Still, integration by parts. Great. Integration by parts. So instead of ft, you can write here t squared, and then what? you take 1 by minus x out of the integration, then the whole integration becomes like this. And you can use integration by parts. Name out u and v. Same as previous one. And you can go through the whole process after class, and after doing the integration by parts, finally you can get a solution. The Laplace transform for the power function. 1 divided by x. The 3, right? And then we no longer divide by 2. How about this? Just t squared. So one thing you can make sure, the order of x should not change. Maybe the coefficient 2 over s power raise coefficient is changed. And all these Laplace transform the original function and the Laplace transform function, each function are listed in the page 23, table 2.1. All the functions we talked are listed in this table, and you can see here. Go through this and open. 14. Third action is what? We call it third action what? Third action of what function? The name. You use third action to describe a function. So this function has a name. A pose, right? You the pose function third action. Then what's the Laplace transform for this? Just 5. How about 1t? 1t is what? The unit step. What the Laplace transform for this? 1 divided by. And you get a ramp function here. So you get then you get 1 divided by square. And see this. And here we come to the exponential function e to the negative at. And we get Laplace transform of 1 divided by s plus a. And how about we get time coefficient times exponential function? This 1 divided by x plus alpha s plus a squared. And find omega t. This should be. How about cosine? Okay. And we talked before the t n equals 2, but we coefficient divided by 2 here. We get the answer is what? 1 divided by x over 3, right? And this shows if we no longer have the coefficient 1 divided by 2, the whole thing becomes what? This is 2, right? And this should be x to the order 3, and it is what? 2. And I color it in red. What I color in red, you should remember. 9 letters. Okay. Last one. And from 10 to 16, this 2 we should memorize. Just what? Sine omega t times the exponential function. And cosine function times exponential function. Yeah, answer is this. See the difference? Still omega, right? But it's no longer x squared. But we should what? Consider the a here. So it becomes x plus a squared. And here, x is no longer x because it should be changing to x plus a. And this becomes x plus a squared. This too. So complicated. The longer is the right. Okay, here it's a knowledge extension. Try to show you guys the figure. From the figure, try to understand the meaning of Laplace transform. No longer have voice here. Anybody help me? The voice is a sound. Oh, okay. Okay, then.
The Laplace transform plays a critical role in engineering, physics, and
Yeah.
mathematics. The Laplace transform allows us to evaluate the stability and frequency response of a system. And the Laplace transform gives us a method for easily solving differential equations. Throughout this video, the color signifies the phase of a function. The phase of a complex number is the angle that the rotating white line makes with the positive real axis. The magnitude of a complex number is the length of the rotating white line. In this function, time does not exist. The input to our function is a complex number with the real and imaginary values along the two axes. The output of our function is also a complex number. It's represented by the height and by the color of the graph. The height of the graph at each point represents the magnitude of the output. The color of the graph at each point represents the phase of the output. This is a function where the output is exactly equal to the input, S. This is the function where the output is equal to 1 divided by the input.
What?
We can specify for what values of the input, S, the function exists. Here, the function exists where the real component of S is greater than 0. This is an example of what we call a frequency domain function. And this example is associated with the following time domain function. A time domain function is simply a function of time. Every time domain function has an associated frequency domain function, which we call its Laplace transform. There is a lot of beauty in this transformation, but to understand it, we need to first talk about the sums of exponentials of complex numbers. For functions of time, the variable s is always a constant. If we increase the imaginary component of s, the white line will rotate faster. If we increase the real component of s, the magnitude will increase more rapidly. If the real component of s is 0, then the magnitude will stay constant. We can multiply our function by a constant. In this example, the constant is the real number 3, but the constant can also be a complex number. Let's now consider what happens when we add exponential functions like these together. The real number comes infinity unless we all functions with time. Time, where s is the constant represented by that point. Each of the exponential functions will be multiplied by a complex number that is the value of the Laplace transform at that point, as was represented by the height and color of the graph at that location. Since there are an infinite number of points, adding a function for each of these points will add up to infinity, unless we also multiply by the extremely small number that represents the interval between each of these points. As the interval between each of the points approaches 0, the sum of all these exponential functions can be represented as shown. We multiply the result by the following constant. We've now created our original function of time. The real number constant c indicates where the line is located.
This definition is called inverse Laplace transform.
You transform fs to ft. We can do Laplace transform. After this, we can do inverse transform. X domain to time.
Okay, then I think, well, this video makes you more sleepy, so let's continue.
Okay, the third part, Laplace transform properties. There are some properties we can use in the Laplace transform mathematical solutions. So the first one, multiplication by a constant to express transform for ft right up and at what is there is a constant a times ft. So what will be the result for the Laplace transform for a ft? Yeah, in terms of fs, where a is constant and where fs we get Laplace transform ft is, then we can write this down. The Laplace transform for the new function a times ft will become 2008 here, and we can take it out of the integration. Integration still get fs and so the final result is what? A times f. So this is called multiplication by a constant. Then take the Laplace transform of multiplying the function by a constant. Remember, it should be a constant. If it's another function, things are not the same, okay? It's equal to multiply its transform by the same constant. Superposition. The transform of the sum of the two functions ft and gt is what? First, and the Laplace transform of ft is upper f, and the transform of gt is what? Upper g. Then how about transform of these two functions sum up? Laplace transform of ft plus gt. Right here, according to definition, we get e to the next power ft and times what? Ft plus gt. Integration in time domain from 0 to infinity. And then we can separate into two parts. One is think about ft, another is about what? gt, and this is what? This is just the definition of fs, right? So here, this is what? GSP. So how about we think about the general superposition problem? How about there is a constant? There are two constants. One times ft, another times gt. Then the Laplace transform is what? A fs plus VJ. This is using what? Refer to what? Yeah, the previous rule we just learned, right? For any constants A and transformable functions ft and gt, and illustration of the superposition problem, we can evaluate all of these.
Plus G equal to GX.
First, we should separate, right? Minus 2, another is 3 times sine 40. And what is the Laplace transform for 2?
So it's gonna be minus 2 over 8.
Two is
But
no,
no,
no. This is a one is a
2x.
constant.
2x.
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 Think about unit step. One is 1 divided by x. Then number is 2.
2 by x.
2 divided by x. Then how about this?
So
You can refer to the table. Refer to look at the table. And this is what this is.
It's gonna be 3 cos 3 cos 3 9
So you can take 3 out of the
16.
yeah, and then work because we get for frequency here is omega. Fine.
Yes.
So this should be omega.
Yeah.
And the x squared plus 4 squared. And we add these two together. Then we get Laplace transform from this coefficient, right? This is how you can use Laplace transform and refer to the table. You can look at the table and according to the rules, you can get final Laplace transform for not the typical common function, but a lot of equations can be divided into sum of what typical common functions. And you find each of the Laplace transform functions and add them together. And we get the final Laplace transform. Differential theory. That's T Laplace transform for ft equals fx. Then take the Laplace transform of n order derivatives of ft. So we take n order derivatives of ft here. Now how about we have Laplace transform for this? Okay, take a look. First, fs times f to the n order, and then f to the order n minus 1 times f0 and it follows. Where f0, f10, n minus 10 are all initial values for all order derivatives of t. So we call it tear. We got a lot of tears of this equation, okay? The common second order differential theorem and first order differential theorem are as follows. Just n is 2. Then we get x squared here, x minus x. Just what? S times x0 and what? The last one is what? F10. Because x order 0 and this is 1. So we just get F1 here. So this is the second order differential theorem. And how about first order? First order, we just have S upper Fs minus. Right? If the F is a gross figure and we have lots of chairs, right? And
The first and S or N S.
yeah, to the last one, S to what? No longer have S, also the final order of the initial value is at n minus 1. From 0, 1 to n minus 1. Okay. But for most of the time, we will have an ideal situation. In words, the initial conditions are all equal to 0. And to say those little tails can be what? Can be the norm. Okay? So things are much easier when we have the ideal situation. Initial conditions are all 0. So we no longer take all the tails. Then what? An order is just what? Take an order derivative of ft, then the Laplace transform for this one under this situation will be like n times f. And how about second one? Just x squared times f. And about the first order, just x times f. Those little tails can be even. So most of the time, we just face the situation. Okay. Try to write it down yourself. But it's already telling you what? Or initial conditions for n order derivatives are what? 0. So it's a very easy one. Try to solve. Something done okay then? You should take math in the first year in class, okay? Don't just use your brain. Write something down, okay? Any volunteer want to come to Blackboard? Any volunteer want to write on Blackboard? No need to hand up, just go to Black. No one? No one? Not sure about your answer? Okay. Give my answer. Oh, you want to see the write this problem down? I turn to the previous page to show you the okay.
Yes, no.
No. During our test, the final test, how long you take a follower sheet?
Yes.
Yes? Just
Table.
an A4 size follower sheet. And you can write the previous followers thing you will use. Not that before?
Okay.
It's an app, in America, call it cheating shit. But no, it's allowed. Okay. Yes.
And ask the students over the internet to do the practice as we do.
Yes.
How can they handle the test? Oh, really? I'm not sure if they're still listening. Okay. We'll go through this together, okay? How about this one? Take it like what? So you have other three derivatives here. So first we should write 5 is constant, right? 5 is still 5. And then you take the other three derivatives. So we have S right after y.
Yes.
To me, this is the unit function, the Laplace transform function, right?
Yes.
And how about last one? Next one? This so easy, right? And this one is what? X, Y, and this 2, Y, it is 4 S X X. And here not working. See, according to the constant of superposition problem and differential theorem, because our initial conditions are here, so they're no longer those tails. So we get a final answer. And this is not working. Oh, we will continue after we take a rest, okay? Can have like 20 for half an hour. How much time you need for rest? 20 minutes, okay? And this is not work. Just stuck. Maybe, I don't know. Oh yeah, it's working. Yeah.
To try.
It's okay then. So right now,
Try again. Let's see.
thank you.
I was thinking because we went time.
It's okay then. But, oh, okay. Try to be on time next time, okay?
So I'm just here.
Okay, it's too small. Which one?
So like the normal integration because like I've has to be like multiplication.
Ah.
Just like you're gonna forget it. It's like different right now. Oh, so because like I was confused about this T like coming like here.
Oh, okay, then you missed the definition part.
Yeah.
So see here, definition is what? If you want to change ft into fs, then we do the integration from time domain 0
Yeah.
infinity. Ft is still ft,
Yeah,
but
it's
we
still-
need to times e to the negative st in time domain. Then see this integration.
Yeah.
After as time goes to the infinity,
Yeah.
t will what? It vanishes.
Yeah, it's gonna vanish.
So this whole thing will become a function just of it, s. See, see.
Yeah.
So don't be late next time. You will miss a lot of things.
Yeah.
Can we continue?
Okay. We have learned differential theorem. So still we have what? Integral theorem. That's LFT equals FFT. FF is what? The Laplace Transform quantity. Then take the Laplace transform of another integral and other integral. So results would be like first FF and 1 divided by s to an order, and then 1, 2, s to an order f minus 1, 0, and the log takes. Yeah. And here, this one are what? Initial conditions of the unordered integral. So if the initial conditions are not given or it's not zero, then the common second order integral theorem and the first order integral theorem are. The order is 2 here. So first we have 1 divided by s2, fs plus 1 divided by s2, and the initial condition of f minus 1, 0 plus, right? How we choose. And how about first? We have 1 divided by s here, and a initial situation. What? Minus 1. Then, when initial conditions are given to you, they are all equal to 0. Then those little pairs can be ignored. That is to say, this one, to this one are all 0. Laplace transform of the above equations are what? Just what? Just fs times 1 divided by f2 and order. And it's order that we say in the word of nt. And second order and first order. And here, this is a very important theorem and very useful. It's called initial value theorem. That ft and its first order derivative have Laplace transform. So the initial value of function ft is what? We take the limitation of ft when t tends to what? 0. So this is called initial, right? You're not start point to when t tends to 0. And this, if we do the limitation no longer in time domain, but in x domain, then the equation changes to limitation of fx. Fx is the Laplace transform of ft. When f tends to what? Infinity. They're not the same, right? 1 is tends to 0. Tends to what? Tends to infinity. And don't forget, it's usually easy for you to make a mistake here. Still we have what? X times f. So if you want to find the initial value in time domain and change to find the final value, then the limitation is no longer take off f, but f times. Don't forget this little. It's just the whole calculation process. It's not real. So this is very unique to memories. So still we have x here. The initial theorem can be used to confirm the initial situation of systems or components. Also can be applied to the impulse response analysis. So thing is, since we have initial values here, we will also have what? Initial values. Think about half of these. When t tends infinity. Why not? After we have 5 values here. Also, let ft and its first order derivative have Laplace transform. So the final value of function continue. We want to find the final value. That is to say, to take limitation of ft, t tends to infinity. We want to do this limitation in x. Things what? We're changing what? X is no longer like t tends to infinity, but opposite tends to 0. And the limitation is take of what? No longer, but what? A little x here still. Don't forget these two little. Okay. The final value theory is frequently applied in the evaluation of steady state errors of control system. So this is applied to the impulse response analysis when the t is very small, the beginning process of the response. And this is used during what situation? Steady state in the curve, the response curve, going to the t tends to infinity as time goes. So let's see two examples. Evaluate the initial value of the function, the exponential function of e to the negative power alpha c. Then how to do this? Yes, it's asking you to find the initial value when t tends to what? Initial tends t tends 0 to 1. And then if you use X domain to solve this problem, then first you should get the Laplace transform of what? X. Get upper, right? And let upper have what? The little x. And do the limitation for fx times x when x tends infinity. And first, take Laplace transform, of course, and then you come to this, right? You can find it in the table. Okay? Then, if you want to take limitation of ft, t tends 0, change it into x domain. X tends infinity. Fx here and little. And then these two together, we get what? S times 1 divided by s plus alpha. And s tends infinity. Thus we can what? S 1 divided by s, s divided by s1 here, and alpha divided by s here, right? And then this is what? When s tends infinity, this is what? Tends to what? 0. Is 0. 0. And in the number, yeah. Not in the denominator, but in the numerator, right? And this is what? 0. 1 plus 0, 1. 1 divided by minus 1. So the answer is example is what? It's 1, right? That's this. Evaluate final value of this function. And ask you to find Laplace transform of this function. And how to deal with this problem. This is you. The Laplace transform of ft is already given, right? Then you just what? Let f times what? X, right? X times f. And x tends to what? The final value of x tends to 0. So it's like this, right? We have x here and the time is here, so this is along this. So we have like this, and when x tends 0, 0, 0. So it should be 5 divided by 2. So these two examples show that how to use initial value theorem and to find the initial value for a function of time, you can change the problem in time domain to what? Domain.
The first one, in this one, initial value of exponential function.
Yeah. Yes. You can just do this, right? And here you don't need to do the test, but you can do from here. Then when t tends what? 0. This is what? 0. So e to the order 0 is just 1. It's so need to use the initial value of value 0, but it's just example how to. You should get the answers using two solutions. So you guys answer the same, right? Okay, shifting theorem in time domain, or we call it delay theorem. Is the Laplace transform of t for any positive real number a. If now it's no longer function of t, but we have a delay here, a t minus a. Then, according to the definition of the Laplace transform, ft is like this, right? And we can have this. If we write this, we can like ft still ft, fs, right? And fa is what? It's just what? A constant, right? And then what? We can write, take the integration of fa, then it's just e f next power an.
Yes.
So this one we can get it Laplace transform at this, right? Well, the function ft minus a is the delay function, which delay time is a compared with the function ft. So how about if this is no longer in time domain, but we had a function here times ft in time domain. So ft times e to the next power at. How about this one? This one we call it shifting theorem in complex domain. Then still you write ft here according to the definition. And e minus at here, right? This two together is this, right? And still times e to the next power ft to do the integration in time domain from 0 to infinity. And these two can be what?
Okay, minus this.
Integrate together, right?
Express.
So the final solution for this integration will be like this. So this is called shifting theorem in complex domain. With the help of the shifting theorem in complex domain, we can write several of the transforms easily from other table. 2.1. See here? Since we have these two, then cos that omega t is like this, right? And if omega cos that omega t times this, then the Laplace transform for this will change to what? It's no longer x, it's what? X plus a. So x here is no longer x, but x plus the same. X squared is what? X plus a squared, right? And same for the sign, but a little bit different as well. The numerator is omega, right? Only denominator changed because x here. So x squared changed to what? X plus a squared. Same with this one, right? Yeah, this group are listed in table 2.5. Partial fraction method. In this section, the partial fraction method is applied to solve the following differential equation. Let's see. This is a differential equation, and this is what? initial conditions. Sometimes they will not tell you by words or by sentence, tell you initial conditions are zero. They will give you equations to show you. But the meaning is the same, right?
Yeah.
Treat it as what? Initial conditions are zero. Then how to solve the following differential equation? First, you should rewrite this into Laplace Transform. Just like this, right? So this should be what? 4x squared upper x. And this is what? Upper x, right? 4 times upper x times x, right? And this is 4 times upper x. Y is what? Y is the what? What function? Y divided by 1x. It's a unit step. Remember the unit step function. This is where you made mistake. So we have here it. Then, and why we write this? Because if we do not know the initial condition, then we should write the whole theorem. We have Taylor's theorem. But because we have initial condition here, so this can be what? 4, right? So we get x close to this. And we want to solve the following differential equation. That is to say, this little x is a function in time domain or x. This is what. So the final answer you want to get is in x domain or time domain. Start from time domain. Then after solving all the problems, you should go back to time. But you see here, okay, change it or do the inverse Laplace transform from x domain to t domain. Yeah, but this is not the typical functions we mostly can look up to the table to find the inverse transform, right? So what you can do, you cannot just directly do the inverse transform. Okay? Then what? By the partial fraction method, one can write the loss distribution in above square bracket. Separate into 2 parts. It's
A.
amplitude of a and a one function. Step function. And amplitude is a, right? And this just divide into 2 parts. And what we don't know is what the number of A, B, C here. We'll separate into 2 and then take it together. The numerator here is like this, right? Get A should times what? A times this, right? Plus what? BS times C times S. C. And 6, the denominator, the numerator here is 1. So this together should be equal to what? So we rearrange the equation according to the order of. So 4A plus B becomes coefficient of x grade. A plus B becomes coefficient of s. and the full A is just a constant. Then in order to make this equal to 1, what conditions can we have? This should be it's just 1 here. So 4A should be 1. In X squared, X no longer is
A should be 1 over.
so we should have 3 equations, right? Then we can solve. A, B, C, 3 coefficients, constant coefficients. Then substitute this to this. See this? If we want to do the inverse Laplace transform, this part can be easily done. This one, this one.
Step.
Yeah, so the value for this is what? Is 1 divided by 4, right? But how about this part? What rules about this? Okay, we take 1 divided by 4 out of the whole. Fast. And this is what you change the numerator into the form. You will easily look up to the table to find out. This is why we do this. So change okay. After we change the equation into the form we want, then you can find this one is the one. You do that, right? And this one is what? It's the e to the negative power t cosine omega t. So we can find this one in the table. So we can do the inverse transform, right? And this one is what? This is cosine, and this is what? Sine. Just leave them. Okay, just leave them.
Yeah, they can unmute again.
See, why we do this whole process to make this equation like this? Because we want to make the equations to the different parts that we can look at to be able to find the inverse transform. And this is sine omega, and this cosine omega. Can still change it to like this. So after we change the equation like this. Then this is what? Just 1. And this is what? E minus 18, 8 what? 1 divided by 8, right? Times cosine omega t. Omega is what? Okay, of 63 divided by 8, right? And this is what? Then, so this just the final solution for the differential equation. So this example that's so complicated. It helps you to understand why we use Laplace transform. Because if you do not know this transform, you just the problem is given to you a very complicated differential equation. You have no ways to solve it, right? But when you use Laplace transform, I then change it to the forms. We know the forms like the common functions. Then we can look up to the table to inverse transform from x domain to time demand, and then together is what? The final solution for the differential equation in time domain. See? Clear? So this, though written in Chinese, we can understand this is the whole process. When we do Laplace transform to solve the differential equation, first we have the differential equation. Next, get what? Laplace transform to what? Laplace transform equation in S domain. And then what? Solve this. Solve the function of x. Then we have the solution, but it's not in time domain. It's in what? S domain. And by change the S domain function into the different parts, we are familiar with just like the common function. Then by look up to the table, do the inverse transform, we get what? The final solution in what? Time domain. And this is just the solution to what? Differential equation. This is the whole closed loop solving process for why we using Laplace transform. So this course does not require to write down all the process for typical common functions, the Laplace transform. Distribution, but memorize commonly used transform. It will help you to quickly solve the problem. Maybe it's during the test, and you will be given a differential equation to ask you to solve, and sometimes you just memorize the common used function, just write it down. Otherwise, you need to look to the table, take a long time. So I can solve. So we can use memorize it or just know how to use the table, how to find typical commonly used function transform. So we just talk about inverse Laplace transform. And this definition is given in that video clip. The process to find original function ft corresponding with the image function fx is so-called inverse Laplace transform. So the definition is this. And here, what the symbol of inverse Laplace transform? Symbol still upright, but we have minus sign. These two come together, become the symbol of inverse Laplace transform. Just upright is what? Laplace transform. But if you do the inverse, you should have a minus sign here. Related form is this. This is the definition. The method to solve the inverse Laplace transforms are for those simple image functions. We can find the original function by table, such as this is a function given to you. Then you can quickly look up to the and do the inverse, right? For those complicated image functions, like the previous complicated examples we just go through. In most engineering projects, we can make the complete image functions into the summation of what? Summation of what? Several simple image functions or several commonly used functions by means of partial fraction method. Firstly, and then according to table, one can find original functions for every image function, unless the sum of those original functions is the result. For example, fs is the image function of the original function ft. One can decompose fs into the summation of several components. Okay? The original function for f1 s is f1t, f2s 2t. Want to do the inverse Laplace transform for f to find its time domain function ft. Then we can find each one's inverse Laplace transform and then do what? Yeah. So this is the inverse Laplace transform for x. Assume that we can write the transform fx as the ratio of two polynomials, bx and ax. According to the order that the order of s. In order to make the above function into partial fraction, we need to rewrite ax denominator into factorial form. One is P1, P2 till Pn are called poles of transform fx. Pi might be real number, and of course can be what? Complex number. And if Pi complex number, they usually come in the form of a pair. Okay? Equation 1 can be shown in the form of partial fraction. If we write fx into several parts, summing together. And this is just what we just do in previous problem. We find the one in ABC, and by make up the equations, we solve the equations and find out what is A, B, C here. And this is A1, A2 in order to make. The method of partial fraction extension to express a null transform fx as a sum of less complicated transform. Using table, we can identify the original functions that correspond to individual transforms in the extension and then use the superposition theorem to write it. So we can see that there are three different situations about the poles. P1, P2, Pn. There are different situations about this. First, all of the poles are different from each other. We call it distinct, right? Also, they are real numbers. Situation 1 is the easy situation. And maybe there are different situations. Situation 2, modify the procedure to include repeated poles. Repeated poles, the same poles, maybe. Where two or more of the quantities are equal. So this is another situation. How about the last one? We have complex numbers coming in the form of a pair of several pairs. So these are three situations you need to deal with. First one, the most simple situation. All the poles are distinct and they are real numbers. Then we can rewrite fx into the pole lines. According to table, at this rate, after we separate into several parts, what do we want to get next? What we want to obtain next? Oh, you can tell the poles by the equation given to you. They are already known. And come to this step. What's the next step? What do we want to obtain next? Right? We want to know the coefficients in each part. Oh, the numerator of each part, right? Okay. We can let s times s minus pk. Pk is a one pole in this whole situation. Then, in order to get AK, multiply both sides of this by the term s minus pk yield this, right? And what? S minus pk can be cancelled, right? That's here. And then have situation. If at this time we get this situation, get this equation, we let f equal to p, then this should be what? 0 no longer exists. And this is what? And this is what? 0. So the general expression for the coefficients is what? Finally, we have this. Just left AK. Take a left plus fs times f minus pk. And at this point, f equal it can be what? First numerator, second to the last one. Okay, maybe still feel confusing but continuous. And we can see by an example. First, x is given to you, right? Asking to do what? Find the inverse transform of this f. You see how many poles in this f? 3. And they were just real numbers. The most easy situation, right? Then, because the denominator is already exactly 4, and the poles are at -1, -2, and -2. Obviously, they are just two real poles that can be by the transform fx in the form, right? And what we don't know right now is what? How to solve. How to solve anyone this. How about A1? If we want to solve A1, then we should let fx times f minus pk. For this pk should be minus A. But first, right? You should minus. You should times this with this. So this are cancelled. What's left is 5x plus 3 divided by this 2, right? And get this equation. Then let f equal to what? pk is -1. So we get -1 here, -1 here, -1 here. After counting this out, we can find A1. And the same process for counting into first, write f as down. And times f plus 1. F plus 1 is f minus pk. Pk is 1 here. P minus 1. So this can be cancelled. What's left is this. And let this. We substitute x equals -1 into this. Then we can calculate final value of A1 is what? -1. How about A2? A2 7%, right? But here, the rest. Here's pk is -2 here. And what we should substitute is x equals to -2. Same for A3. So after we obtain the value of A1, A2, A3, then substitute those coefficients we calculate into the equation of. Then let's become this. This is easy to look at the table to find the inverse transform. This one is really no clear. Sine cosine has clear. It's just that there should be exponential. Right? So it's a function of e, right? Yes. What? Still confusing? Yeah. Sometimes it will come to problem and the solving process are given to you. You can easily understand. But when the time comes to you to let yourself write down the problem, things are why it's so difficult. If that seems little bit difficult for you to write down something.
That's why like it
So
was.
that to hold. And actually, we can deal with situation 2 and situation 3. But I don't think that's really for you because the whole solving process are so complicated. I think we have easy one to deal with the problems of all situations. How? Think about this one, right? Oh no. See this? About this. Think about the easy solution for this. But not easy, but easy to understand. I don't have it right here. And write like this here. If we don't use the situation 1, if we don't consider about different situations, we just use one solution for all different situations. Then how? See this? If we do this, let's see. We just have them together. Then how about A1? 2 times 1. Right?
See, that is that's class 3. Then the function is that we read this line.
This A2 is 1, right?
The denominator. Yeah, that's one. That's class 3. This class.
Oh. Right?
Yes.
Over right here, right? Okay.
Yeah.
Then what's next? We just focus on the numerator, denominator. Numerator, sorry. And this is what? A1 is square root. X. A2 times S3. It works. S3 yes plus 2. And we can rearrange the equation by the order of s. So s squared we have what? 1 A2 and for s we have what? 5A1 A2 A3, right? How about the constant? What? 6A1 plus 3 plus 2A3. We have these 3, right? Then let's go back to the original fx. What is the coefficients for x squared? Does we have x squared here?
0.
So this should be what?
0.
This should be what?
0.
How about this? And this one. We can solve equations together. Then we can have what? right? Maybe you can write it yourself to see if by this solution, can we get the same answers at this one? So this seems you need to do more math, but it doesn't upon what? Different situations. If we have complex numbers, or we have the repeated poles, we can still use this, right? Right? So can you quickly work out the values of A1, A2, A3? As long as the process I'm writing is right, so you can get the right answers. Here, have a rest here. You can fill this out and we'll talk later, okay?
How can you be making noise?
It was. Talking to you, you find out I can't be what we say. Try to have some respect. Respect you like a lady.
To you,
I will also.
Just come and touch me, don't throw it on the pay.
Why did you throw my pen there?
And because you just throw it to me.
that doesn't matter. You guys.
I'm not sorry shit.
It's okay.
Coming and then touch me like that, you try that one, don't be scared.
Okay. Yeah.
It's okay.
You think, wow.
Oh, exactly.
Like,
And student, like, can you just respect me, just try to touch me and then, no. Send the language. Send the involved.
Hey, full name of Chinese name.
And the mechanical thing.
I'll send it there on
No one. No.
I don't think it can be hard.
Ah. That's
No, thank you.
Explain which one you are doing. Which one is
I spent so much. Okay. First.
Now, yeah, what I'm gonna ask you when you come out, so.
I can understand.
And go away, keep going.
Yeah, you can understand then, like, oh, you know,
I can give it to you understand.
Of course, I understand what you guys say.
And it's what?
Stop. Stop.
it's like some people like this, they can just go like somewhere and then like on the bed and stand up and then you know,
Guys, I'm all down. Oh, guys, all down wrong way.
You guys.
I'm all saying. What was your point for you to fail with that?
You already say the next time. Say that. Whatever. Say.
Me go somewhere. That's a joke, man. Me
I'm
go
not saying. I'm like.
bro, you get you man.
Oh, oh. Stop right now. Oh.
I think you said anyone that tell you, but
Okay, finish. Okay, finish. You are meant by you argue today. Okay, maybe you say before you ban.
they need some attention, they can just go somewhere and place in the console.
Okay, you know.
Somebody is doing you.
I don't like to see him.
No,
Because you can say that's
Yeah.
what you know.
love,
Working.
I know what to expect. I know.
love, you know, like the one respect for this.
Yes, you already called them. The next time she did that, okay.
It's waiting for this.
That's it.
How about the answers? The same.
Yeah. We have 11 in classroom, so we should have like 33 over internet. But including me, when they're all in 26, and how many are missing? 45, right? Including me. Oh, yes, they're in different time zones, right?
Yeah.
They're nice over there. You see, yeah, I forgot there were time zones. Oh. So after you solve the 3 equations together, you will get a1 equals to 1. A2 A3 minus. So it's the same in this one, right? So if you're not sure how to use this kind of way to solve, then you can use the do it way.
Can you like because of this way? You can use it to solve the situation.
Yeah. I will show you next, okay? But first, try to solve this problem yourself. It's easy. You just need to separate this everything into 2 parts. Have how many holes here? 2. If they're digit, they're real numbers. 1 minus 1, another 2 minus 4. So try to work this out yourself.
can use different ways to solve it. Up to you. Okay.
that difficult?
First, you need to separate it into two parts. You need two different poles. Y is -1, another is -4. So we should rewrite fs into the form like this. So there are two unknown figures we want to figure out. One is a1 for poles equals -1. Another is a2 for poles equals -4. And if we use the way previously in our points, then we will according to this refer to this formula. Then a1 should be the whole fs times x plus 1. This is cancel and the let x be -1. We will figure out what and a1 is 2. And set for a2. Write fs times x plus 4. Cancel, cancel, and now let x be -4. So we get a2 equals -3. And substitute these two answers into fx. Then we have this. And this is if you do inverse transform, this should be exponential. This exponential function too. So we will get t like 2 times e minus t and 3 minus 3. Minus 3 times e minus 40, right? And of course 40 that's bigger. Should be bigger. Okay, 50. And how about if it's the way? Show me black. How about to deal with the way? The way we here, let's see.
Still, the first steps are the same, right?
And after we write this, turn them together. So we get I'm not S squared here, just start with S, right?
Yes.
What's the coefficient of x? It's -1. So we have a1s plus a2s plus minus. And we have another equation. Times a1 plus a2 equals 1. Right? And these two solve together, we get what? A1 is should be A1 2. What? A1 should be
Yes.
no. It's 2.
Yes.
1 because we have x here, so okay, maybe that just
Because it's 1 over 1. Yeah. 1 minus 1 times 2.
Then right? No matter which way you use, you should get the same answer.
okay, repeat pose. I don't think this solution is that easy to So let's just see the example. Next example, how many poles this
Four
poles
is four.
four
Is one is zero
0
minus two minus two twice.
yeah here minus 3 right?
Yes.
Then how to solve this? No longer situation one, so 32.
Try.
Let me try.
You want to try it? Okay, try it first, then I will show you.
Solution.
Since you're so interested in this course.
Oh, here are two students saying they're facing problems with internet. And after class, they can see the videos and PowerPoints. Internet, right? Oh. Do we still need VPN to see YouTube, right? We cannot just link to YouTube.
Friends, how to deal with the repeat. How many parts should we divide with this MX? Four. 2 x plus 3 and x plus 3 is 23.
How many parts? How many parts you divide? 4.
Yes.
See,
Yes. 9.
from the direction of S, 1.5 repeat post is 2 posts. So we should reason. The equation should be written as. No. So maybe you see here,
Yes.
first part. X, okay. X plus 2 is okay. Then X plus 3 is okay. Why does this answer plus 3? You just have 2 X plus 3 here, right? Then y can come together in the same equation. Because if you write x plus 3, they are actually have the same denominator. So you just need a 1. But here things are different. You should write x plus 3 and repeat it. You could just write down the square. Then how to get a1, a2, b1, b2.
It's necessary like the names of B, A.
It's okay, just add a line.
If I take A.
So it's just you write B and A, just telling they're different. They are repeat posted. They're repeat. Just in case you make it, but the people like me, whatever you like. Okay. About 18. Then 18. Because 18 here and what? For a pair of repeated posts, right? So here, you should type no longer x plus 3, but x plus 3 squared. So here cancel. That is 1 divided by x times x plus 3. And here, let x be minus 3. Substituting into this, we get minus 1 and minus 3. So we get 1 divided by 3 or 2. This is for sure. And how about A1? A1 is very complicated to figure out. You should take derivative of this. And after we take derivative of this, and then we have x equal to minus 3 here, substitute to this, we will find A1 is 4 divided by 1.
So while what is so
It's just not required for you to know just to memorize, to try to know how to do this. But I don't think it's an easy way. Because if we have repeat pose like not just square all the receipt, then you take derivative like 6 and 7. So it's so complicated to define a solution. So way. So maybe I will introduce a next solution for you. And here, let's just go through this. But for B1 and B2, since we're looking at right, and substitute what you figure out into the final we get this. But can we use this kind of? Can we? First, the first 2 steps are the same, right? What we make sure is we want to separate the fs into 1, 2, 3, 4, 4 parts. And the denominator for each class is take pose and the repeat pose and the square of the repeat pose. And we get A2, A1, B1, B1 to by using the way we just use. Of course, we just what? You no longer need to write x plus 3 here because it's included in square. See? This times this, but this is no need to touch again because we have square. So how about this one?
just like the same.
Yeah, just A2 is S2, S2. And how about A1? We have S plus 3, right? And S plus 2. And then for what? And then you can do what? Rearrange according to the order of S and compare it with this one. So what do you get? You should get equations together like maybe from the order of like S3, right? S2, S and R constant. Right? We have 4 unknown constants and we have 4 equations. Can we solve it together? Each one? By solving this together, you will get A1, A2, B1, B2. See? But maybe the math process is a little bit hard to solve. Don't make a mistake.
but process is just the same. No matter they're distinct pose or repeated pose. Or maybe this math is so complicated, so that people still make it much easier one. How about this one? Try to use solution in Blackboard to solve this one. First, you should separate this whole fx into how many parts? Three. One is x plus 5. Another is x plus 2. And the last one is x plus 2 squared. And each part has its own coefficient work, has its own numerator. You name it whatever you like. A1 into A3. And you add this. Right here, and do it together to check if we are in the same answer. Am I right?
Get confidence.
Huh? That's according to the S order.
This is to go for I plus two also right?
Yeah,
And then B is to go for
because B already has S plus 2, so
so
we only times S plus 5 and S plus 2 for B, right?
nothing A C
Sheet A is equal to 2, A2, A1 is equal to 2, A2 is equal to 1, A3 is equal to -1.
It's really good. You see, if the repeated pair is just a pair, so the order should be 2, right? So you can use this kind of solution when you to solve. This is when the order is greater than 2 or 3, then this kind of solution becomes complicated. This solution seems easy, but the math is hard to solve. And no matter which way you use, as long as you're doing right, you should get the same answers, right?
Yeah.
you send that
Okay, I will put. Then how about this one? They're just repeated posts, no longer this distinct posts. So first, of course,
when you serve that sorry, you get some else.
of course you should, as long as you're correct. Maybe you make some mistake during the process. Just check, maybe okay, or maybe I correct something wrong here. There anything wrong here?
This should be done something like
Okay. For this one. This one. Okay.
So which you should look up to table and find this one. This one. Of course, we should separate the whole fs into three. One is plus one, another is plus one squared, and the x plus one order and three, right? If the order is greater than 2, we take second order derivative of this whole thing, and then we should times this. So the formula is complicated when the order is greater than 2. And this is not required. Let's do the exercise.
Please repeat me the way you find it.
This one.
Yeah.
So I will use PowerPoint. Yeah. Right now. Okay. So this exercise also is easiest one. Visiting host.
Yeah.
Just two. I'm trying to write on this. The coefficients were 2 parts minus 1. Here.
These nine. You want one.
A1 is minus 1, A2 is 2.
And we will have one. Okay.
Yes.
Same with this. And you can use both ways.
You can like First, you can times what? X plus 2. Answer. And the left x plus 1 divided by x plus 3. Let x be what? Minus 2. So we'll go minus 2 over minus 1 and this minus 2. So we get a 1 equal to minus 1. Now, for x plus 3 here, cancel, and let x be what? Minus 3. We will get a2 equal to 2. And we will get this. Okay, let's see this. Solution is already showing here. Solving the following differential equation by using Laplace Transform and initial conditions are given. They're all equations. So to choose. Then first, you should write this into Laplace Transform. You will have how about the second order derivative? We have x squared here and 2 times x times and just operate. And this is the points usually make this game. 1 is 1. Don't just write 1. 1 Laplace transform for 1 is what? 1 divided by x because it's otherwise unit step function. It's not a constant, okay?
Yeah.
And then x would be what? Solve this for x. X is this. And you see this, how to get x function, original function in time domain. You need to do inverse transform, right? Then how to do inverse transform? The first step you should do is to separate this into the commonly used functions. So you see, this has a pair of repeated poles, which is x equal to what? Minus 1. So you separate this into 3 parts. One is 1 divided by x. Another, maybe these 2 coefficients are not known. First, write it down and solve for each. And you separate this into this and solve for each coefficient. And then do inverse transform for each part. This is what? Just 1, right? And this is what? This. See? You have squared here, so you should have t times exponential function. So this, according to this, we get this left here. How about this one? Minus 1 times e to the negative power t. So this is what? Solution for differential equation. Okay, that's all for today. And we have assignment. Turn to page 36. 36. No problem. 2.2. This is a very easy one for you. For those who have this textbook, please camera it and help me upload the problem to. See what? Yeah, it's a sign. Okay, hand me your assignment homework last week. Okay, next week. Okay. Okay. To write down. Yeah, I will.
I just want to take a picture.
Okay, okay. Oh, I already write down the answer in my textbook, so
Okay.
so
I wanna just buy the book.
so for homework, maybe check someone else.
Okay, no,
I already have the answer. I write down the answer, so
okay,
it's
no,
not okay for you to take picture.
fine.
Those who are over the internet, today's class is over. See you then.
All right, okay. All right, okay.